In this lecture, we're going to talk about flow rates. Flow rates are extremely important in the environmental engineering world. Mass does not stay stationary, things move and things flow in the real world. So we're going to talk about a couple key terms that we're going to use throughout the semester. So a flow rate is a rate at which material moves from one place to another. So it is an amount per unit time. So a flow rate, because it is a rate, is per unit time always. That's a little bit different, right? So an amount would be something like mass. A flow rate would be something like mass rate or mass flow rate. So they're slightly different. Mass would be something like kilograms. Mass flow rate would be something like kilograms per second. And that brings us right to our next bullet point, right? So mass flow rate, for the purposes of this class, is going to be defined as mass per unit time. It's going to have units of things like kilograms per second, but it could have units of things like grams per hour. As long as it's an amount per unit time, that is a mass flow rate. And for the purposes of this class, we use the symbol M with a dot over it to represent a mass flow rate. So anything with a dot over the top is a flow rate and not an amount. If it doesn't have the dot, it's just an amount, and that's important. So you may actually recognize this from calculus. A mass flow rate is the same thing as dm dt. So it's the change in mass per unit time. So from calculus, dm dt, it's the derivative, right, of if you had some kind of a mass moving forward in the system. We can also have a volumetric flow rate, and volumetric flow rates are going to appear a lot during class. So this is volume per unit time. So it's always a volume, something in units of, say, meters cubed per second, or it could be liters per second. Anything where it's a volume per unit time is a volumetric flow rate. We're going to use V with a dot over the top to represent volumetric flow rates this semester. And if you wanted to use the calculus version of that, that's dV dt, a change in volume over a change in time. And the reason that this is important for us is that it's actually easier to measure volumetric flow. It's very easy to measure the volume of water that moves through something, but it's very hard to actually measure the mass as it flows. We can measure mass itself, but mass flow is actually very difficult to measure. So often we use a volumetric flow, V, to get an M, to get a mass, and we use the density to do that. So that's why we talked about density in the last lecture, because density is a relationship between mass and volume. So if we can always measure volume and we know the density of the substance, we can then find the mass of the substance. And I'm saying this in terms of just volume and mass, but it's also true for volumetric flow rate and mass flow rate, because a volumetric flow rate and a mass flow rate are going to be per unit time. And so those units of time are actually going to cancel each other out, and then we can use that density relationship again. So that's going to be really, really critical. Always remember that your mass and your volume are related. The other thing that I want to talk about related to flow rate is how we measure flow in the field. So this is not necessarily something we're going to do during this semester, but it's kind of nice to know how we actually measure flow. And there are two types of flow meters that are very, very common in the field. The first is called a rotometer. It's a tapered vertical tube that has a float, and a float is just a piece of material that moves up and down in the liquid. It's good for larger flow rates, and as the larger flow rate goes up, that float goes higher and higher in the tube. We can also have what's called an orifice meter, and this measures the pressure drop across an orifice. At a larger flow rate, we're going to see a larger pressure drop. So it's actually easier if we take a look at what those look like, right? So a rotometer is just that tapered tube which has the little float inside of it, and as the flow increases, that float is going to move up in the rotometer, and then we correlate that change in height to a specific flow. And then an orifice meter is basically going to have that little gap in the middle. Let me grab my laser pointer so you can see. All right, here's a little orifice, and then there's a manometer down here which basically measures the pressure drop in the system as it moves through that orifice. So it's a way of looking at how does that flow change as it goes through a specific spot. And that's going to be it in terms of flow. Make sure you understand that it is per unit time when we talk about rates, and that's going to be really critical moving forward.